This video is going to show you the solution to an example problem where we're going to find the net magnetic field at a point in space from two current carrying wires. We're going to make it kind of simple and not find it off at any irregular angle, but just the basic idea, the basic concept behind it. So begin with a little explanation about current though. Physics is about the study of matter, energy, motion, and force. And we know that when we talk about energy, objects flow from high potential to low potential. So in this case, we're carrying energy along in our circuit from the positive terminal of a battery, which is at higher potential, to the negative terminal, which is at lower potential. So to do that, we're going to have this current, these flow of charges delivering energy to whatever our device is. So the current's used to represent that flow of energy. Therefore, if that's true, then energy is flowing from positive to negative. If energy flows from positive to negative, then positive charges are what we're going to use to represent the current, or the flow of energy. So that's why we're going to use positive charges as the flow of energy. In our explanation, we're going to talk about the right-hand rule and not the left-hand rule. So if you're using negative charges, you're actually applying what's called the left-hand rule. But now we've kind of converted it over to talk about the flow of positive charges and the right-hand rule. So if you're thinking about looking at current as the flow of electrons or negative charges, this particular presentation may not really help you a whole lot. Two wires are separated by 10 centimeters. And I've got them down here as gray and a pink. I've got one current coming out of the page with a gray wire, and the X shows current going into the page and the pink wire. So the dots mean stuff coming out, the X's mean stuff going in. The wire on the left, the gray one, is 15 amps, and the wire on the right carries 11 amps. That's the pink one. Each wire is 5 centimeters long. Find the B field exactly in between them. So to find out the strength of the B field at some distance away from a current carrying wire, we're going to use Ampere's law. So in this case, I've got the closed right-hand rule, and I've got my thumb representing the current coming out of the page, and there's my right hand, and I can see the direction of the magnetic field, and that it's going up in the middle of the page. For the other one, I've got it going into the page using the closed right-hand rule, and I can see the circulation of the wire. It's also going up. Because the two B fields go in the same direction, I'm going to add the two B fields due to each wire to find the total. If I got a situation where the B fields went in an opposite direction, I would subtract. I would take the B field going up minus the B field going down, and I would know that if my answer is positive, it matches the positive direction. If it's negative, then it matches the negative direction, which in that case would have been down, with up minus down. But back to our reality, our problem has both of them going in the same direction, which is upwards. So now I know the directions, and because they go the same directions, I'm just going to add them up to find the total B field. So now let's figure out how big these arrows are. So here are my B fields. There's one from the pink wire and the one on the right from the gray wire. Now what I need to do next is I know that the total B field in between is going to just add up the two B fields because they point in the same direction. So I'll find out the magnitude of the B field due to the wire on the right. That's going to be the pink wire, and that's mu naught times the pink wire's current divided by 2 pi r, where r is the distance from the wire to this point in space, which in this case is 5 centimeters. So to the right, it's mu naught times 15 amps divided by 2 pi, and the distance is 5 centimeters to the point in space. For the gray wire, it's mu naught I divided by 2 pi r, and that's going to be mu naught times 11 amps divided by 2 pi times the distance to that point in space. Since I figured out earlier I've got to add them up, I'll just go ahead and do a little bit of math and add them all up, and I get my total B field to be going upwards at 1.04 times 10⁻⁴ teslas, and that's at the point midway between the two wires.